Great, thank you very much, David. A few bits of introductory stuff before we go along. I'm broadcasting from Ken's new audio-visual facilities. This is the baptism, I guess, by fire a little bit of getting our facilities going here. But yeah, we do things here in a very independent way because we're a very independent sort of company, and we are based now, or have been for quite a while, on a little farm just outside the town of Faversham in Kent. So you should see on the first overhead, that's where we are now. And the reason that we were able to find such a nice place in the Kent countryside, pronounced always with care, is that it's now 20 years since we first discovered and purchased the farm, and it was in a much more rundown and derelict state. So we're very fortunate having our own premises. And also, because of a variety of strange historical reasons, I ended up setting Ken pretty much on my own. So at the moment, it's my own personal business. Now, one of the issues about this, just this morning, I had here a piece of paper. This is the second such letter that I've received this month. Dear Mr. Thomas, we have been engaged by a number of highly acquisitive businesses, including PLCs, privately owned companies, and private equity firms, to identify potential acquisition and inward investment opportunities that fit their specific criteria of interest, and believe Cairn Research Limited could be a potential fit. I'm keen to have a discussion regarding your thoughts on the potential of a full or partial sale, as a wide range of options are available to shareholders, such as yourself, when constructing future business plans. Well, here is the option that we are going to be following, because I'm very pleased to announce that things are very now well in hand for us becoming an employee-owned company, which means the ownership will be distributed amongst everyone who works here, and that means we can effectively stay independent in our own premises on our own farm for as long as we want to, and that means that we can serve you as customers for as long as we want to. This may or may not seem much odd to you, but over the years, I think we've all seen a variety of rather promising companies just get bought out for various reasons, and then sooner or later, at least in our view, they get trashed. So I just want to get this very firm message that we've been around for a while, and we intend to stay around in our current form for a whole while longer. Right, end of silly speech. So light sources. Well, I've been giving this talk for almost as long as we've been at the farm. So the first time I gave this talk was in Plymouth in 2003. And at that time, light sources were far less advanced than they are now. And I was having perhaps to try and make a boring subject sound interesting. Now, the challenge is the other way. If I'm not careful, I can make a very interesting subject potentially rather boring, but I'll try not to. There are some very important fundamental points about light sources, both in general, but in particular for getting light into microscopes, because a microscope as seen by a light source isn't quite the same sort of animal at all as seen from a preparation. So in fact, as we'll see, it's actually quite difficult to get light into a microscope. So I'm going to start off talking a quick background of quantification of optical energy, which is a bit of a mess, then characteristics of some of the practical sources, and then coupling to microscopes, which is perhaps the heart of the talk, then wavelength selection, and then finally at the end, or other bits and pieces during the talk, I will talk about structured illumination, where you're illuminating only part of a preparation at the same time. Now, although this is a general talk, it's very much the emphasis is going to be on fluorescence. As David said, I cut my teeth on absorbance indicators, but fluorescence has become a much more widely used and easier thing to deal with, because if you have something that fluoresces, you get a signal that wasn't there before, whereas with absorbance, you have either more or less light coming through. Now, we are, in respect of doing all of this stuff, we are very much misled by the properties of our own eyes, unfortunately. So you'll see in the bottom right-hand corner of this next overhead, this is the rough spectral dependence of the human eye. So we're much more sensitive, for around between 500 and 600 nanometers around the green and so on than we are at either in the blue or in the red. Whereas for those of us who are wanting, of course, to use these things for instrumentation purposes, what you want is a flatter spectral response. So I'll come on to that because this is, again, a real nub of the talk. Broad spectrum sources aren't easy to come by, actually. So the most important thing is when you're dealing with things as judged by the human eye, then the unit that you use is the lumen, which has actually been spectrally modified, if you like, so that a lumen of blue light looks the same as a lumen of red light, but the difference there is that you will have very much less actual relative power in your light source at these mid-wavelengths because your eye is much more sensitive. And I'm going to be showing in a future overhead something which isn't so widely known and should make the point. Otherwise, yes, we've got most important other point here is the size of the emitting source. So this is effectively a radiant intensity, which is a emission in terms of lumens, or what's better to use because then you can equate those much more easily to the number of photons, as I've shown down the bottom right of the overhead. However, bearing in mind that blue photons are about twice as energetic as red photons, so a watt of blue light is only going to have half as many photons as a watt of red light. And if you really want to get perverse, as Britain is being dragged kicking and screaming back into the 19th century with this Brexit nonsense, and you see where we've nailed our colors on this one, then we may have to go back to these really old imperial measurements of the foot candle and so on, just to show that Britain can still dominate the world with all this rubbish stuff. Now, most traditional way of making photons is to heat something up. And this is how the sun works, and this is how incandescent light sources work, or should I say used to work, because they've been very much displaced by the other methods of doing things. Now, the issue here is that if you heat something up, then it starts glowing, it starts emitting photons, but you have to get it pretty hot in order to shift the spectral range of emissions, then go red hot, white hot, etc., up to the visual wavelengths. So the issue with the sun, for example, is it has its maximum emission at 500 nanometers or thereabouts, and you can equate that to the temperature of what's radiating, which is, of course, the surface of the sun rather than deeper inside. And you have, therefore, an equivalent temperature, 5,800 degrees, something that emits uniformly at all wavelengths according to that relation is known as a black body. So although, of course, the sun is far from black, but it is behaving in that general sort of way. So the issue, therefore, is if you're trying to make photons yourself by heating things up, most things are, by the time you get to 3,500 degrees, even tungsten has given out. So in order to generate thermally light at the sort of spectral range we want, you basically have to heat up a gas. Now, some of this stuff has become more superseded by later light sources, lasers, solid state ones, that is, and LEDs, but nevertheless, there's something about some of these arc lamps which remains very, very useful. So on the left here, I've shown a xenon arc spectrum. And the important thing there is, apart from a few wobbles around 500 nanometers or so, around there, and a lot of guff out at the longer red wavelengths, it's relatively broad spectrum. So all the way from UV right down to near infrared. So this is quite good. Mercury, on the other hand, makes the Alps look flat. So it tends to concentrate its emission over a range of wavelengths over certain narrow ranges, which aren't always so useful. In particular, there's this big gap between around 500–600 nanometers, or down in here, which is a big problem. Also, mercury is very nasty. The lamps tend to fail relatively quickly, and when they fail, they might explode and fill your lab with mercury vapor. So the take-home message here is xenon, as I'll show, is going to continue for certain applications to be quite useful, whereas mercury has probably had its day. There's various other intermediate types of sources of this sort where whatever the gas is has been impregnated with certain other metals and so on to give extra peaks, but it's basically a bit of a mess. Now, actually, Cairns, a very brief aside, Cairn got into all of this rather by accident, because if you remember your inorganic chemistry, you'll know that xenon in particular is a noble gas. So how can you pass a current through it? It's got to ionize. Well, the answer is if you heat it up enough, then it will ionize, and then you can pass current. However, in order to do that, you have to put in an initial spark of some tens of thousands of volts. And when we were starting to provide this sort of equipment for fluorescence measurements, it turned out that people's amplifiers and so on were being destroyed by this electromagnetic pulse. And also we found that the electronics being provided by companies who are making this stuff as well were very poor and unstable. So even though this was, at the time, it was a mature technology, we actually had to get in and do our own versions of this. And in fact, again, these things are worth bearing in mind if you do need anything of this sort. This shows a stability graph from a xenon arc lamp. This is what can be done. And you can see that over a minute or so, you've got a stability if you put it as RMS, which is the standard way of doing it. It's better than or about 1 part in 1,000. That may not sound very good, but in practice, it's wonderful because of the statistical nature of light itself. In order to measure light with 1 part in 1,000 accuracy, you actually have to get the square of that number of photons in your time period. So that's 1 million. So this is actually way better than you could get away with doing. Now, LEDs. These, since I started giving this talk, have come on from strength to strength. And you see in presentation, or if you do your Google search of nice graphs and so on, you will see versions of this particular graph here, where you've got lovely individual peaks of all the different wavelengths that you might need. And this particular thing I want to show, the black one, you'll see is actually comprised of something in the blue, and then there's this rather bigger or broader, shall we say, longer wavelength peak. What they've done there is coat a blue emitter with a phosphor, which is taking in some of that blue light and re-emitting at longer wavelengths. Now, because of the cruddy nature of our eyes with that really rather limp response, best at around 500 nanometers and not so good either side, and we've only got 3 different color receptors in our eyes anyway. So if you get the balance of that all right, it looks white. And so this is great for regular illumination, but as a broad spectrum source, it's clearly not as good as you might like. And then the real issue, I had to work quite hard to find this graph. This is where the sort of best examples of the LEDs at different wavelengths have been put on the same scale. And you can see, yeah, red's good. What's been particularly interested in the blue and the near UV, they are really extremely good. Very roughly, although you can't quite compare chalk and cheese too much, but yeah, in practical use, these things out here are about 10 times as bright as a xenon source working on equivalent bandwidth and so on, with caveats. Whereas if you look at all these apparently interesting wavelengths in here, in absolute terms, the levels are completely rubbish. So you might, in practice, might be better off actually using one of these white LEDs and filtering out those wavelengths that you don't want. LEDs, though, can be, in a sense, they're unstable, but in a much more important sense, they can be made very stable indeed. To a first approximation, the level of light from an LED is proportional to current, but there may be odd things going on at low currents, and at higher currents, they will tend to saturate to a certain extent. And at still higher current, they just go bang, so you have to buy another one. That's another advantage because they really are much cheaper than the arc lamps. However, what you can do, because they have intrinsically very fast response times. So within feedback loops, you can get them responding, linearizing up within just a few microseconds. If you digitally switch them, they can be way faster than that. Now, what happens, and what this graph is purporting to show, is if you pulse an LED on and off, then what's occurring is that while you're passing current, the LED chip itself is tending to heat up. And a lot of people don't always appreciate when you're talking about the temperature of the LED, you're not talking about necessarily the temperature of the housing, you're talking about the temperature of the actual chip in there. And although you need very good thermal bonding, as good as possible, to the housing, the fact is that if you put more light into it, then the thermal gradient between the chip and the housing will go up. And this is what's going to determine ultimately the maximum current you can put through. So there's a time constant with this heating up, and it's effectively just a few milliseconds. What we got here is this is, I think, 50 milliseconds, or it's 5 milliseconds per division. And you can see the important point is the yellow is the drive current, and the blue is the optical response. And you can see on the left, it goes up, and then there's a little bit of a tail back. That's a 505. At 590, it's orange. This is one of those rubbish LEDs, to be honest. You can see there's much more temperature sensitivity, so it's dragging back quite a lot. However, if you put a photodiode and a feedback loop so that you adjust the current so that it stays the same light output, you can see with both of these, you can linearize them up very well. Perhaps a more useful aspect of this isn't so much at high currents, but if you're doing more quantitative work, then you can control your LED intensity over many orders of magnitude. So this is a particularly cool thing to do if you want to, although for fluorescence excitation, we're normally interested in hammering these things as hard as we can. Next up, lasers. Now, Gail McConnell will be talking about lasers later in the course, so I'm not going to steal her thunder at all. There is some kinship with diodes in the sense that a lot of these lasers nowadays are actually a form of solid state diode. So they do tend to have the same sort of range of wavelengths available that are equivalent to the LED. So that in particular means you're struggling quite a lot between about 520 and I think 630 nanometers to get good diode type lasers. For people who want wavelengths in between, then there's various other more complicated ways of doing things which involve stuff like frequency doubling and what have you. So lasers for those intervening wavelengths do exist, but they're just not as convenient and therefore inexpensive to use. So what we've shown here is just basically you've got a load of different lasers, wavelengths along here, and they're all being combined with dichroic mirrors. So they're all coming out to a single fiber. Now, I'm going to get now onto the part of the talk where I'm going to be doing a little bit of basic optics. The reason for this is to do with what I said earlier on, that it's not as easy to get light into a microscope as you might think. It's a bit like having to shoot light back down into the barrel of the gun rather than coming out from where the actual bullet would be. So this means that in practice, what you need to get a lot of light into a light source is literally to shine light through a tunnel. And what that also entails is that the light has got to stay as parallel as possible when it's going through the tunnel. And that in turn means that it has to have come from a relatively compact source, because if you take light and you make it into a parallel beam from a single point, then it stays collimated forever. However, if your source is extended at all, then what is going to happen as it goes past being collimated, it's just going to spread out. So we're therefore particularly interested in having a system which can collect over a wide range of angles from your source to be as efficient as possible, but to collimate as well as possible. So in terms of the basic optics, the shortcomings you have of the optical system itself are the form of these three aberrations: spherical aberration, coma, and astigmatism. And then we've also got the field curvature is akin to astigmatism. Distortion is just that. It doesn't really matter at all in this context. But what we're going to see is that spherical aberration and coma are going to be rather limiting factors in terms of how good you can make the optics. And perhaps rather surprisingly, it's coma which is going to be the difficult one. As you increase the range of angles that you want to get from your ideal point source, then you have to have a big range of angles here to collimate, and that aperture, that's the aperture. And then the other thing, the H, is the size of the source, which you'd like to be as small as possible, but it will still be finite. So the biggest problem potentially, you might think, is spherical aberration, because it's going to cause your beam in practice to spread out a lot more than it might have done otherwise, because it increases with the cube of the aperture. Whereas coma doesn't sound quite so bad, it's just the square of the aperture. And if you're on axis, there is no coma, because this H is this term here, so a single point on the axis will only have spherical aberration. However, the sting in the tail of all this is to do with the coma, as we'll come on to in a moment. But first, I just want to equate for you the difference between numerical aperture and F numbers. The most important point here is that they're effectively measuring the same thing, but one of them, the so-called F number, this is what you're tending to use for distant objects, where your object is a very long way away, and it's just the ratio of the aperture to the focal length of your optical collecting system. Whereas in a microscope, you're dealing with finite objects and finite image distances. So under these circumstances, you tend to use this number, which is the sine rather than the tangent. So it's only using the half angle rather than the full thing. So there's a factor of 2 in there. And that effectively, once the small angles, the sine and the tangent become the same. So these then become equivalent. Now, the big problem for all of this is the NA. Everyone looks at a microscope and says, oh yes, that's a very high NA device, because you look at the NA of the objective, which, yeah, of course, it can be above 1 because of this N, which is the refractive index of the medium in which the thing is working. Otherwise, you would be limited to an NA of 1, but of course, you can get up to 1.4, 1.5 for certain things. So that's great. You think, wonderful. However, what happens, your objective is magnifying, and there's a very straightforward relation here, which is what's the NA coming out of the other end of the back of the objective, and it's the NA coming in divided by the magnification. So what this means is, if you have, say, a times 100 objective, let's say an NA of 1, just to make it simple, then the NA coming out of the back of the thing is 0.01. So you're therefore dealing with something. If you look at this, it's going to be only a very, very narrow range of angles. So it's very nearly collimated. So this is why these aberrations become very important, because to the extent that they mess up the collimation you're going to need to get light, actually, as you'll see, you need to get it back into the objective for epi-illumination, for fluorescence, which I'll explain in a moment, but even for regular illumination, where you're using a device known as a condenser, you're going to have the same problem. So here is what spherical aberration is. As you increase the diameter of the beam relative to its focal distance, then the more extreme rays, instead of being focused to a point, you get this sort of trumpet type arrangement because the more extreme rays get focused closer. Coma is the real weird one. It's weird in all sorts of funny ways, but it's effectively a variation of magnification with aperture. So shown here where as you've got to have the light coming in at an angle, otherwise you won't see this effect. But here you can see that the coming in, when you come in at an angle, these more extreme rays are missing your so-called paraxial focus. So there is nevertheless, you can get a partway solution through this sort of situation because you can use an aspheric lens, which sounds really the answer to everything. Although, of course, it's, as we'll see, it's not necessarily that straightforward. So this is shown actually with arc lamps. But here, the important thing about arc lamps is that you get a very tight, the emission point of the arc lamp. If I just go back, where are we? Oh, arc lamp profile. Yes, point I just wanted to reintroduce you. Here, I mentioned this the spark you needed to get the lamp to discharge. This distance between here and here is only 1 millimeter, but in practice, you get a hot ball of plasma right by this lower electrode. So the size of your emitting source in an arc lamp is wonderfully small. So that's very good from the point of view of getting a lamp light in. It's better than LEDs in that respect generally. So here I've shown an arc lamp and an aspheric lens in this case. There's a problem with making aspheric surfaces, but if you just have these old-fashioned cheap projectors, I'm not sure to what extent they still exist nowadays, but you can have a cheap blob of glass here, which will collimate reasonably well and get light from your arc. And then you can also, with these, play quite a trick, which is have a hemispherical surface, which takes the light coming from the back of the arc and makes an image of the arc right next to it. So it doubles the size of the source, but it might give you something approaching twice as much light. Now, an interesting point here is it's good to be able to replace the lenses with mirrors because you get, first of all, no chromatic aberration. And secondly, you can get these really rather extreme profiles that can apparently do very wonderful things. So there's a bit of history here because this is the sort of light source we still do sell for xenon, actually. But there were two sorts that we made. One which with the arc lamp vertical here and a ellipsoidal mirror behind it. Ellipsoidal, by the way, is just a particular form of what's generally known as a conic section. It's equivalent, or not equivalent to, but it's part of a family of which a parabolic reflector is one extreme, where you just get something which is completely collimated. However, if you bend the thing around a bit more, then you get a second focus. So this can be quite handy. As you'll see later when I briefly talk about our monochromator, to be able to get light directly focused from a mirror behind. Now, but the interesting thing, at least for us, was that you can also have this type of arrangement where instead of just collecting light front and behind, why not wrap the mirror all the way around and then you can collect the whole lot. So this indeed does overall collect several times more light. But there's a problem. And this is because of coma. You see, only those mirrors work in the way that's shown only if the light source is vanishingly small. So here I've shown some typical numbers. Here is a reflector. Here's the source, and there's the reflector, and it's going to then send light forward. Effectively, what we're doing here for the optics is running the system backwards. So we start with a column, the optical design, we have a perfectly collimated beam and then see how compact we can form the image. And if it's on axis, then it's nothing. But this is something with a 200 millimeter diameter, 100 millimeter focal length. And yeah, on axis, it's perfect. But even one, get something out here, you can see that as long, once your image is displaced by just 1 millimeter, suddenly you're getting over a millimeter of, in this case, coma. So they're no longer perfect. Oh, just as a little quick advert, these things were done in ZMAX some years ago. And ZMAX is now an awful lot more expensive than it was in those days. So it's probably out of the price range of ordinary mortals. So also, yes, the real issue is they want several $1,000s a year for you to rent the software rather than buy it. So if you fancy having still something your own, we found this otherwise doesn't seem to be too well known. I've shown it on there, something called Optalix, which is very much cheaper, and it can read and write ZMAX files. So bear that in mind if you have any optical interests. Oops, sorry, the double hit. So here is a somewhat more extreme mirror here, where we've made the diameter 300 millimeters, focal length 100 millimeters. And now look, this coma is like 5 millimeters of stuff. So this is pretty poor. And if you compare with what we were showing there, you can see this is absolutely dreadful. So the light source that we were basing for that particular form, the light source we were basing it on had a rather expensive diamond-turned mirror around the thing. Whereas the situation with this, there was so much coma, you didn't need a precision reflecting surface at all. You could instead just have, basically, we had cheap molded reflector. So that was quite fun to do. Right, next part is how you get light into a microscope with particular reference to fluorescence, but this is a particularly nice diagram from Olympus, which shows an upright, sorry, oh, thank you, yeah. I don't normally get caught out with phones this way, but we had to have an emergency phone link to get this talk going. Yeah, so throw it in a bucket of water. So yes, what we've got here is the way you illuminate for fluorescence, which is known as epi-illumination. I guess doubtless you all know all this stuff, but nevertheless, for the record, I will go through it. So you have a fluorescence excitation source along here, and then underneath you've got a conventional transmission illumination. And it used to be that the old filament lamps were going to be quite good enough for looking at transmission illumination, whereas here this is clearly showing an arc lamp. You'll notice also, why have they got several lenses here where just one or two will do? When my tongue is a bit firmer in my cheek, that's saying, well, because it's an optical designer, if you do anything too simple, then people will kick sand in your face, where you really got to have as many optical components as necessary to impress your friends and relations. But there is a good reason, and that is in order to preserve this very tight spot that you need in order to efficiently illuminate the microscope. So what you're basically doing is to, in a refractive sense like this, you share the bending between a number of surfaces, and that gives you lower aberrations overall than trying to do it all in one go. So the important point I just want to show here is that you've really got quite a narrow path going through. So it's very important that you get as good collimation as possible to get light into the objective. Now, this is, of course, an upright microscope where the optics is rather simpler. Most people will be using inverted microscopes, so that the light is therefore to go around rather more corners. But I think this shows perhaps a little bit more clearly what's happening. And then you've got this wonderful device here, which is a dichroic mirror, which reflects the shorter wavelength excitation into the objective, then excites preparation, and then it comes back and all directions basically, but then the objective picks up as much as possible of it, which will do it with a high numerical aperture device, but nevertheless making it much more collimated coming back through. And then these longer fluorescence emission wavelengths can come through, and then you can view with eyepieces, or you can have one or more cameras to actually do some instrumentation on it. Now, what I've tried to do here is simplify the optics as much as possible, because this is ultimately what it's all about. And it's become clear to me over the years, because I sort of do this stuff for a living. It's become second nature to me, but it's not at perhaps first viewing that you realize what the fundamental issues here are. So I've reduced your objective to a single lens, and it's got a rear aperture, an objective pupil, and this is sort of shown as correct as I can. So you can always model the objective itself has got a whole bundle of lenses in there, but basically you have a distance from the equivalent single lens to the sample, and then you've got a distance which is going to be the same for good reason to the rear aperture or the objective pupil. And then you get, for normal surface, you get a magnification, which is basically the object distance to the image distance. Note that I've not shown any infinity optics or any of that stuff in between, because that just complicates matters. The fundamentals of the system are nicely reflected in just the simple stuff I've shown here. So if we start with just imagining you're viewing a sample, then I've shown top, bottom, central parts of the sample, and then they will be brought to a focus at this field iris position, so top edge, center, bottom edge. Now, the fundamental important point here is that field iris may not actually be present in your system physically, but it's always going to be effectively there. In that, this is the most important point, especially when you're using this backwards, then you're illuminating the field iris, or where it would be, and then focusing onto the sample, get a nice load of light there. However, you look at it this way, supposing you have some light coming, remember it's coming backwards now, and it's falling outside the field iris or where its effective position and size are, then it might get through the objective. It will then be that much further above or below your field of view. On the other hand, the more obvious type of situation you've got is there is a very real iris. Well, it's not an adjustable one, it's the hole in the back of the objective, to put it crudely. And clearly, in order to get light going into that, then you must avoid a situation where you're over illuminating it. I don't know if I can quickly show on our LED system. Yes, there we are. Just don't worry about the blue for the moment. I don't know how easily that is to see. Oh, there's a nice, yeah. That is an image of the LED itself. And the most important point is that showing up on, yeah. There we are. Whoops. There. We're still feeling our way with our audio visuals here. Yeah, it's rather overloading the camera, but I can see a white spot, and that's relatively big actually. So this is the issue. You can imagine if you've got an objective, say with a 10mm rear aperture, then not all of that is going to get into the objective. So what you might think is, why don't you just have the light converging more strongly to get it through. I'm getting slightly ahead of myself here because the best way of doing things in order to get more even illumination of your objective is to take the light source, which you see has this structure, and instead of focusing it to get through the field iris, you focus it to get an image onto the objective pupil here. And then when you do that, then I've shown the three, I'm using the three colors here now for the three positions. So you are focusing light coming down through here, and just showing how light gets to the top edge, through the center of the objective pupil and down the bottom edge. You can see I've drawn this as accurately as I can, and you can see that this light, instead of being imaged as just the reverse of the excitation of pathway there, it's now forming collimated beams where the angle of the beam relative to the optical axis is dependent on how close you are to these edges. Now, this is a fundamental limit of the objective because you're not going to be able to get light that's hitting beyond these points because it's going to hit a big buffer. But if you then say, oh, never mind, this is the real thing that catches people out, let's just focus it down more tightly, then the effect of that would be, bear in mind that your field iris may not be physically present. So what then happens, yes, your objective may well be able to take the light if you're starting from here and here, but then these collimated beams from these individual points will all be that much wider. So although you can get the light into the objective, it won't be exciting the part of the field of view that you can actually see. And if you're just sticking some sort of optical sensor on the bottom of your objective and say, oh, yeah, that's better. Well, it might be, but it might not be. So if anyone is doing any quantitative measurements on this, I think it's very important to have a real field iris in the system so you know exactly how much is getting to what part of the field. And just a slight ahead of time here, talking about one aspect of structured illumination is thanks to Kevin Webb at University of Nottingham. And to go back, what we're picking up here is the following. You're seeing here that light that's gone through, that's been focused onto the rear aperture, or the pupil of the objective, is collimated beam. So what Kevin has done is use this issue in reverse. So he starts with a collimated beam. In fact, he has a ring, but multiple rings of LEDs, which are some significant distance away. And then these are focused by the effect of the objective itself into the back focal plane, basically the same as that back aperture of the objective, where for phase contrast, you have this device known as a phase ring. It's basically just a piece of glass which has been etched so that it is slightly thinner where you have this ring part of it, and this causes a type of interference that converts refractive index differences into intensity differences. So this is taken from Kevin's paper. It shows the basic principle. So there's an image of the LED ring there. Compared with how you normally do phase contrast, you have to have a close-up device, a condenser, which is providing your illumination and really close to it, to the sample. Whereas with this method, you can have something which is much further away, and particularly this is really intended for inverted microscopes. So your microscope stage will be down here. That's your phase illumination. You can still do all your fluorescence stuff in the normal way, but this gives you a lot of access for electrodes or any other instruments of torture that you're applying to your preparation. So this is quite a neat thing. Right, now I'm going to talk about wavelength selection. The important point here, which is not, I think, at all obvious in advance, is that it turns out, thanks to optical interference effects, that you can have very high degrees of wavelength discrimination. And this is, of course, vital importance for fluorescence measurements, because you're putting in photons by the bucketful, if your light source allows you to do so. And then you're trying to eke out that small, relatively small number of emitted photons. So what you, again, to just hop back if I dare, whoops, here we are. This device, the dichroic mirror, has to selectively reflect the excitation wavelengths and transmit the emitted ones, which they do reasonably well within an order of magnitude or so. So if I just show what is going on here, is actually a double excitation, double emission setup. So the green line is the transmission through your dichroic. So it's transmitting these wavelengths between here and here, where you've got that red line, and it's transmitting these here, which are that's the emission from the first beam that we've got here. Now the vital point here is, if you see the response to the dichroic mirror, it's okay, it's not wonderful. And yet what is not so obvious, there's an excitation filter and an emission filter. This is known as a FITC-TRITC set, so for fluorescein and rhodamine, basically. But the important point is that you want as little light as possible that is in the excitation light to get through to your emission. And what this doesn't show is that you can have several, maybe many orders of magnitude of discrimination between in-band and out-of-band. How it's done is way beyond my pay grade, but basically you've got stacks of interference films, shall we say, stacks of thin film through which there's optical interference, and they're so calculated in terms of their composition and thickness that some wavelengths come through constructively and some destructively. So overall here, we've got a system where it provides light in this excitation range, sort of 400 to 500 nanometers for fluorescein excitation, and then from 500 to 540 or so, that's your emission range for your fluorescein. Then you come in with a rhodamine-based dye, which is exciting around about 540, 550, and so on. And then you've got emission filter here for getting its emission around about 600 or thereabouts. So it's not, to me, it is not obvious that these filters can be as good as they are. But fortunately, this is what allows many cool things to be done. However, those things are fixed, and for many circumstances, you may want to have a situation being able to dial up whatever wavelength you want. So we're about to start talking about a monochromator. This was something that we're still making. One of our competitors, Till, fell subject to this, I think effectively twice. So although it's not such a big market, it's now much more to ourselves. And the way this operates is, again, it's by interference, where you have a reflective surface, which I've shown here in cyan, and then you're illuminating with white light, which I've shown here as yellow, so you've got a mixture of wavelengths. If this was a plain mirror, all the light would come back straight through. However, because of this sawtooth structure of the reflection, then by straightforward geometric construction, that you get an additional, call it reflection, but in fact, the real name is, of course, diffraction, such that there's a one wavelength difference between the beam that is reflected from this tooth and with this tooth. So you get constructive interference. And because a wavelength of red light is longer than a wavelength of blue light, then there's path difference, which gives you this massive, big enhancement of constructive interference. It's wavelength dependent. So it's really all, in theory, it's very straightforward. And in practice, these things can be done to the most enormous precision for detailed spectroscopic analysis, although for our sort of fluorescence experiments, we don't need anything quite so exotic. But this is how a monochromator works. So you actually need to have, again, for very similar reasons, to have effectively a point source, but because we're working only in one dimension rather than two, then we can have a slit rather than a point. So again, you need to get a good monochromator response, then you need to have a light source with a very small equivalent spot size. So this is why we're still from time to time selling xenon light sources, because this is exactly the type of light source that you need in order to do this particular trick. So focus the light through this slit, and then you use a mirror rather than a lens to avoid chromatic effects. So you make a collimated beam, shine it onto the diffraction grating. So now as your diffracted wavelengths like so, you refocus those second mirror, and instead of a single image now, you put broad light through it, you'll see a spectrum here, but different wavelengths being focused to different points on the exit slit. And by rotating this grating, which you can do very quickly with something known as a Galvo drive, sort of millisecond time scale, then you can select which wavelengths are going out through the exit slit and which are then going to be used for your preparation. Now I'm going to say, to finish off a little bit about selective illumination, or structured illumination, to give it a better word. There's a device, I'm sorry, I've not got an overhead to show the device itself, but it's quite easy to describe. These things known as DMDs, or digital micro mirror devices. What they are, they're made actually by the same sort of semiconductor processes that you would use to make camera chips. Whereas instead of each pixel being a detector, it's actually a very small mirror, a few microns across. And by electrostatic means, then that mirror can be tilted one way or the other way, reference to a straight ahead reflection. Yeah, the laws of physics are actually very size dependent. We don't realize this except when you see stupid phrases like, if a flea was our size, it could jump over a house. No, because of how the law's scale of flea was our size, the poor thing couldn't even stand up. So this is because of how dimensions, scale, volume goes up with the cube, areas with a square, and so on. So the practicalities of this is that whereas with our monochromator, we're struggling to move that, be it still, a grating maybe that sort of size in a millisecond or so. If you're trying to move a little mirror, which is only a few microns across by an electric field, then that time scale is now measured in microseconds. So these things are very fast. What you do in order to use them for selective excitation is you basically project an image of your DMD onto your sample projector, whatever it is, and then you have light coming in at some angle, which has to be quite relatively steep, around 24 degrees. So pixels are either flipped this way or this way. If a pixel is flipped this way, at half that angle to 12 degrees, then you get very powerful reflection and you get an image. On the other hand, if the thing is tilted the other way, then the light goes way off into wide blue yonder. So that is very much an off pixel. So there's a variety of instruments have been available over the years where you can use them to selectively excite any part of your microscope image. Now that's all easy, in a sense it's easy, straightforward, but us being us, we've tried to be a little bit difficult and more cussive because we're trying to get the thing to work the other way around. This is one of those things that's almost jinxed us at times because we'd originally started doing this sort of thing with via collaboration, but sometimes collaborations work, and sometimes you end up going alone. And this is what's happened with us. But the challenge for us has been not just to illuminate selectively, but then to take that light that's been caught back and use it for confocal detection. So this is what I've shown here. For excitation, there's an excitation source as dichroic. And then there's some weird optics which we won't worry about for the moment, but that just introduces the light at this 12-degree angle. The interesting thing is we've got the opposite arrangement here, so that when a pixel, as I say, one of these little micro mirrors, it's one way or the other way, then it's going to be on for one source and off for the other, and vice versa. So that part, we figured all this stuff for the moment, is sort of straightforward. And then this is just relaying optics to get into your microscope. Okay, so that would be effectively the objective there. And this is just stuff to get the light round corners to your image. So you now have your unsuspecting photons being collected back as fluorescence emission coming this way, and now they are being gathered. This is the horrible part, because they're being reflected at angles of plus or minus 24 degrees, and yet you've got to try and get images from light which has been collected at that angle. So what that means, if you've got light coming back like this, you can't have your detector like that. Your detector has got to be like this. And that's a big problem in the sense that detectors aren't really designed to take light at these extreme angles. So we use a trick with a couple of spherical mirrors, one of which is concave here, and the other one tucked in there is convex concave. It's a rather interesting set of things, but there's an optical axis change. That means by the time the light gets to the cameras, which are here, that effectively that tilt has been taken out. So they now hit the camera straight on. As I say, with this tongue-in-cheek here, it's all done by mirrors. So because of the way the optics works, the path lengths overall are quite long. So here's your tiny little DMD. Yeah, nothing is so wonderfully straightforward as you might hope. So with these DMDs, I'm showing that they're tilting this way, and so on. Whereas actually the tilt is over a diagonal axis. So in order to get a left-right swap for the tilting movement, and we put the little DMD display at 45 degrees, so that we don't have all the detector optics that way. Yeah, we got I think three of these systems out there working as prototypes at the moment. The main issue is that in order to present these things to a wider public, we're going to need a fair amount of software. But that is being worked on in a variety of different ways, in particular from Elliot Steele at the Ashley Cadby's lab at University of Sheffield. So this is some stuff that they did probably a couple of years ago now. But the most important thing, which is what really attracted our interest in the first place, is this business of getting what you're known as the non-conjugate image. So for regular confocal, just forget you've got one light source here, and it's going through, exciting around there, and then you come back. Now your fluorescence emission light, if it goes through or if it reaches the same pixels, micro mirrors, that it had on the way in, that straightforwardly is a confocal image. However, some of the light that comes back will fall on other micro mirrors, and from that you can actually construct a second image, which is literally the complement of the first, because if you add the two up, you get something that's basically a bright field image. So you can see that that is potentially a very intriguing thing to do. So in the third little overhead there, if you selectively illuminate this heart-shaped thing on your prep, and then you look at what's coming down the other side, then you'll see you get this dark area. So add them up, and you get your wide field image. And this has a variety of potentially handy things that you can do for image reconstruction. So yeah, that we are involved actually in a whole variety of related software projects and hardware projects you'll hear about in due course. This is to do with Micromanager, and some of this stuff is going to be running on that. You'll probably get the flavor of my view of these corporate world, that we are very much public domain, open source type of people here at Cairn. So yeah, we're happy to make money, but we're not after making monopolies or doing all of this sort of corporate rubbish. I forget how long. I think I might have spoken more or less to time. I hope people are still here, because I'm very much talking to myself for most of this. But,
so there are plenty of people still connected, at least according to the numbers, Martin. So the numbers are polite, and one has disconnected, so I think he waited for you to finish, or for me to start.
Yeah.
And you finished according to schedule, which means you spoke for less time than you were allotted, because we started a little bit late. So that's
yeah. I did rush through a little bit, just
perfect for us. So I don't know if there are any questions. So people have been asking questions in the Q&A, and some idiot called Boris has been trying to answer them. So you might try and review them and see if the said person has given at all sensible answers. So there was a question about the efficiency of LEDs compared to arc lamps. So I said they were much more efficient at the correct wavelengths, but heat production could still be an issue. And the follow-up answer was that it would be an issue limiting the amount of light produced, and also potentially heating or bleaching the preparation.
Yes, as I said during the talk, one has to be rather careful comparing things in rather different ways, because with a monochromator, at least something like ours, you can choose what your bandwidth is going to be either side of a center wavelength, and then you've got to then sort of compare that with what the actual individual LEDs are doing. But I would say, as a rule of thumb, from our autumn Plymouth stuff, looking at this overhead here, that in sort of the practical conditions, the relative level that you can get with a xenon light source and our monochromator be around about this level. So to get your order of magnitude right within an order of magnitude, so to speak, then I would say these near UV LEDs can get us a good 10 times more light, useful excitation light through than we can get equivalently with the monochromator. So that means it's loads. These things.
Okay, those curves are a little bit misleading, in the sense that the high peaks are also much narrower. So usually that's what you want, but not always, I guess. Yeah.
Well, yes, indeed, that's another important issue. So yeah, you can argue, well, argue around the houses, but I've been really quite taken aback by, for example, 365 or 385
right.
LEDs, just how humongously bright that they are. Yeah. But no, point is taken, because as part of my backpedaling, I was sort of half hinting that even in order to get within an order of magnitude, then we were probably having, with a monochromator, a 25 nanometer bandwidth. Also, yes, I didn't touch on this in specific detail. I think I mentioned on the monochromator slide, which there we are, that the spectral response you get, wait for it, there we are, yes. You're forming an image of the input slit on the exit slit. So these are a square. So as you go either side of your central wavelength, you imagine an image of the input slit sliding across the exit slit. But to a first approximation, you're going to get a central point where everything goes through. And then according to what the slit width is, once you're moved by a slit width one side, or would there be half a slit width one side or a slit width the other side, then you're going to have what's basically a triangular bandpass profile. So what is normally quoted as the bandwidth is known as the full width half maximum. So if you have 500 nanometers and 10 nanometer bandwidth, that would mean that it would be 50% at 490 and 510 nanometers, and going down to 0% at 520 and 480 nanometers.
Okay, there was another question that I tried to answer approximately. Dichroic mirrors, what would be a typical reflection to transmission ratio, you know, in or out of bandpass? I said 100-fold, but you can design pretty much anything you want.
Yeah, basically, again, let's try and find that overhead.
I also said usually you try to do most of the work with the emission and illumination.
Oh yes, yes, absolutely. Yeah, if you look at the green curve here, you can see that it's not nearly as tight as these other things. I think the answer is, if you want to have specific band pass and notches, whatever, you could probably do better than that. But I think there's no question that the workhorse of all of these things is the filters. Another point I didn't have time to get on to, where you have to be rather careful, is your dichroic is actually in the light path at 40, wait for it, actually in the light path at 45 degrees. This makes its spectral performance really much more critically dependent on the angle than if you've got something which is straight ahead. And if your interference filters for excitation and emission are going to be straight ahead. And the other aspect of having something angled like this is you get polarization sensitivity. So if you want to have dichroic mirrors that work well at all polarizations, then you will effectively have to pay extra. But that's one of a number of reasons why you're much better off trying to pile your selectivity into the excitation and emission filters rather than the dichroic.
Okay, yeah, that's a good point. A dichroic is defined to work at a specific angle of incident light. So there are a couple more questions have come up. So I'll read it to you. You can maybe read it yourself, but is it just the property of a diffraction grating surface that reflects the different colors of light in different angles, or a normal mirror also does so?
Richard Feynman was one of those amazing people who could see things from an entirely different perspective. And his description of how a normal mirror would work is that in principle, light's falling on it, and it's in a sense that the photons are then trying to go at every conceivable angle. But because of destructive interference, in terms of all the many paths that an individual photon could take, if you have a plane mirror surface, all of those paths cancel out, apart from that one, which is reflection. As soon as you start messing around with the surface, and a good way of seeing this is if you imagine that your mirror, instead of being continuous, and forget those teeth on as I showed it there, because that's to do with trying to direct light more towards more favorable angles. But yes, if you take away half your mirror, but in the form of a whole series of narrow stripes, that also will convert it to a diffraction grating. And that's actually effectively blown the lid on what is happening, because some of those destructive interference pathways that prevented light from doing anything other than what we would call a straightforward reflection. Suddenly those become possible.
Okay.
So literally Alice through the looking glass in that respect.
Okay, so there's one more question at the moment. The timing is pretty much perfect. So it's a more general question about the differences in particular in terms of efficiency between using lasers or LEDs.
Yes, I left using lasers very much to Gail McConnell.
Coming lecture.
Yeah, but no, this is a very important point, because the decent laser, you have this wonderful approximation to a point source. So all of this business of you basically got complete control over what you do with your apertures and so on, because you have the almost ideal of a true point source, so you don't get this sort of diffusion effect. Yeah, if you can see this, oh yeah, you can see me. That is clearly a sort of blurry blob. If that were a laser, you would see a tiny point, and that point would be going on for some very considerable distance. So it's not an issue for that aspect of it, is not an issue for lasers. But lasers do have certain problems of their own. They're obviously the more expensive, and you may not get all the wavelengths that you would ideally like to have. But yeah, nevertheless, they are really good. And I would mention, oh yeah, if I do something very slightly corporate for a minute, I do make rather fun of all these increasing numbers of LED light sources, which consist of what I call a shoebox full of multiple LEDs with a light guide coming out at the end. And they really do tend then to be really rather expensive for what you get. What we're trying to do with our own stuff here is to have individual LEDs that you can then put together in more of a Lego type of way. So this is a more economical type of coupling system to connect multiple LEDs of whatever wavelengths that you want. But if you really, I forget the prices, but one of the things that we distribute is called the LDI, which stands for the Laser Digital Illuminator. And that is a series of very intense but economical lasers made by our American friends, partners, 89 North. And if you really want to have a good multi-wavelength light source, then it's probably a good idea to check out their prices compared with these shoeboxes full of LEDs, as I rather disparagingly call them.
Okay, maybe just a general point to make in terms of efficiency is the efficiency of light generation is rarely an issue. It all happens a long way from the preparation. If you need more light, you can just spend a bit more money and generate more light. But of course, lasers are a lot more expensive than LEDs. So there's a rather specific question about replacing parts on a Zeiss confocal. I think that's probably not Martin's job to answer for Zeiss confocal microscopes, so maybe, although maybe he's happy to modify them.
Well, Zeiss are very much a sort of not invented here company. They do go their own sweet way, and bless them. But in terms of collaborations, harmonies, and so on, we've always found that Nikon and Olympus are the easier companies to work with.
Right. You'd probably, Anna, you'd probably need to address that question to Zeiss. With replacing a confocal light source is probably quite a constrained application anyway. I mean, in principle, it would be nice to do and it should be easy to do, but it's in the Zeiss, although it's not going to be part of the confocal system, as that's going to be the laser illumination. So it's probably for the transmitted light. You probably could.
I think that would be something if Zeiss themselves were to approach us on any of this, then of course we could help. But to try and get involved with Zeiss microscopes at the customer level is probably tricky. It might be doable, but we don't have the practical experience that we do with the Japanese companies.
Okay. Depends a little bit what the lamp is doing in the microscope, basically. Okay,
yes.
So I think that's the questions that have come in so far have been answered. I think people will be able to find the company website, and of course can ask you about all your products if they want, and see what is on offer. So there are
one other thing, I'm not sure I mentioned my hype here, but thanks to the idiocy of Brexit, it's be useful for people to know, not just that we're telling these corporate idiots to go away, but we are in the process, in fact, it's pretty much in place now, of setting up a German office in Heidelberg.
Okay.
And there will be one or two proper German speakers there as well. So although I speak very bad German indeed, but I have some comprehension of the language. But yes, anyone wants to deal with Ken, there will be real Germans at the other end.
Okay, so no customs problems in Europe anyway.
Not for you, not for European customers. We're having to take all that on the chin.
Okay, so I think we'll stop there. Thank you very much, Martin and Andy. And